Yeah, thanks for the kind introduction. My name is Zhiwen, and I'm currently an assistant professor from Texas A&M University. So today's topic is about vision language model augmented with the instruction aligned 3D reconstruction. So the motivation of this work is kind of clear and simple. So how to enhance the 3D perception capability of vision language models. Yeah, so let's take an example. So this is how current vision language model doing with the 3D perception. Say giving the monocular video as input and having the language instruction. So we will have some questions, and we hope the language model can answer our question properly. Some models we do see many concurrent work that, let's say, from 3D LM and the 3D VLM. They are either use the additional depth sensor for each input image, or use the pre-built 3D map, just like this, to first build the 3D model from the monocular video and then feed the 3D input to the language model. Yeah, that's how it works. But there are two questions. Say if we are requiring the depth sensor for every video, it's not scalable because for most of the web video, we don't have the accurate metric depths. And we also don't have a global map from the monocular video plus the depth sensor if we rely on this side. And if we are using the algorithm, let's say start from motion or SLAM, to first build the 3D map, 3D point, global 3D point from the monocular video, and then tokenize the 3D point into the language model. It's also variable, but the point is traditional 3D reconstruction is very slow. Say if we have a room size environment to do the reconstruction, we require, say, roughly several minutes to several hours for the reconstruction using, say, 100 images. That's a typical case for the 3D reconstruction. So both of the directions are not that scalable. So it is possible to pursue a scalable way to enhance the vision language model with the accurate 3D perception. That's a key idea of this work. So let's take an overview of the 3D perception and reconstruction pipeline in the view of traditional algorithm. So give the multi-view image as input, just like here, we have two images as an example, and our goal is to build the semantic 3D map, just like this. Okay, so we first do feature extraction from the input images, and after the feature extraction, we got the correspondence from these input images, and we do feature matching. So after feature matching, we can estimate the camera pose, the relative camera pose between these two, and we will know where we got these captures, right? And subsequently, we will do the triangulation and sparse reconstruction to get a set of sparse 3D point clouds. And with this 3D point cloud, then we will perform dense 3D reconstruction. Sometimes we call it as stereo matching or 3D Gaussian splitting reconstruction, something like that, or NERV. And finally, we will perform semantic understanding because do the dense reconstruction alone do not provide any information about the semantics and the instance. So that's why we will use some semantic understanding model upon the build a dense 3D model. And finally, we will use this semantic 3D map for many downstream tasks, like say the robotic navigation, autonomous driving, and decision making. Yeah, so that's a very typical procedure from raw images to semantic 3D map. You can see they are stage-wise, and that's why the error will accumulate from the first step to the last, because it's very difficult to calibrate if they are non-differentiable. And this long pipeline also make the real-time performance infeasible. So we have multiple modules and they cannot communicate with each other, and they also very slow. I mean, for each step, they cannot make a real-time pipeline. And if we stack them together, we we require, say, minutes to hours of post-processing to get the 3D map. So that's a question and overview. So let's first take a look at how to build a 3D dense 3D map, and we can first review at the multi-view geometry, which is a very typical way to get the dense 3D map or perform dense 3D reconstruction. And the multi-view geometry is also the foundation for many 3D reconstruction, generation, and understanding. So imagine we have this physical world is in the real world, and it's in the real world, and we got two captures from viewpoint 1 and viewpoint 2. So having the physical world and we got these two capture, we have the two images, and we want to rely on these two images alone to recover the 3D geometry. So we have to do some assumptions. Let's say first assumption that exists in the real world is for a single 3D point, like here, when we project onto multiple image plane, like this and this, and if we track the cross-view consistency, so we can recover the 3D information from images. So that's a basic assumption, and that's how we use 3D reconstruction to recover the 3D model from image input. And we will first introduce a work from NUX last year to introduce how we can make the 3D reconstruction into a differentiable model, and then discuss how can we align the encoder, the 3D encoder, with the existing VLM model. So the motivation of all my previous work is very clear, because we're living in the 3D physical world. Everything around us, say ranging from autonomous driving, robotics, and extended reality, we rely on the geometry and spatial relationship to make decisions, to make the interaction with the physical world. So that's why we have to allow the computing system to first being aware about the 3D perception, and then make interaction with the physical world. And if we take a look at how real world works, let's say we have the static 3D environment, like the building, like the house, and we have some dynamic subject, like human, like the moving vehicle, and human, the observer, will have a camera, and at the different angles, we take these captures. So there are 2D images, or you can think that's a monocular video. So with this video, we can recover the 3D and the motion. And with the recovered 3D information, so the sensors and devices, let's say the mobile phone, the extended reality headset, and the drone, and the robot autonomous driving, many sensors that have to rely on the perceived 3D information and then interact with the human. Yeah, so that's how it works in general. And the traditional multi-view geometry, say, because we don't know the depth information, so here we will make some assumptions, right? So after making the assumption, we will try to estimate. Let's say if we want to estimate the depth map of this image, so we need to estimate the probability from this depth plan to the last depth plan. So because we don't know about any depth information, we will assume some depth hypothesis and then make the prediction. So as we have introduced in the previous slides, so we will track the multi-view consistency. In multi-view geometry, maybe 10 years ago, so people trying to start to use the convolutional neural network to warp from the left image to the right image. And we will find the cross-view consistency. So we call it as warping. And we will build something called cost volume. Say this is X and Y dimension. And we also have the assumed all depth hypothesis in this axis. So we don't know the depth. So that's why we have some assumption. See here, we have 5 depth plan. And after that, we will make the estimation of each step's probability. And the MESNet also proposed to use not only the raw pixel, but also use the feature map from the latent layers. But let's first look at how the dense 3D map can give us. So this is from my previous work 5 years ago. So we designed a new cost volume about based on the MESNet. So with this new cost volume formulation, we can first make the 3D reconstruction for city scale reconstruction. Yeah. So here you can see we have images of this city, and we build the dense 3D map, the point cloud of this city. And it indeed carry a very rich information. We have the point cloud for every subject we are interested with. Yeah, so this work is called cascade cost volume, and because it is with a high efficiency, so many subsequent work will adapt our cost volume formulation to their application. Yeah, so that's an introduction of a very early of my previous work. But let's jump to this large spatial model work, which is published in the New York last year. So the motivation of this work is how can we unify all of these steps together into a single differentiable neural network, right? So here we have the input image, and our goal is to obtain the semantic 3D map for downstreaming tasks. So how can we use a transformer model to do them into a unified model? So that's a high-level motivation. And our solution is we can use a neural network as backbone, as a prediction of the 3D map, and use neural rendering as the objective function. So here is our solution. Give the raw images, we will use a transformer model, which is differentiable, of course. And we do the 3D reconstruction, we build a 3D map, like say 3D Gaussian spreading. So we reverse the 3D Gaussian attributes, and then we will render at another viewpoint, say the viewpoint 2. So we flatten from 3D to 2D, and then we will compare between the rendered image and the observed image. We will compute the difference between the pixel intensity, and we will update the model. Yeah, so here is the workflow. Give the first input images, and we have the neural network. We have the transformer to predict the 3D model, and we flatten from 3D to 2D at a new unseen view, and we will compare the difference during the training to optimize the model. So here is a point. This way, we only need to annotate about the camera pose. So how we transform from the raw images to the view 2, and in this way, we can update the model very efficiently because we only require the annotation of camera pose, the relative camera pose from the here to view 2. Yeah. So which means if we can build this system ideally, we only need sparse camera pose annotation to make the model to predict 3D. And here is our solution. So first, we have stereo input, 2 images from different angle, and we first initialize our geometry from a previous paper called Dust3R. And there is a subsequent work I think most of you will be more familiar with, VGGT. VGT went by the paper in the CVPR this year, and I think it's a subsequent work based on the Duster. Yeah, so Duster make the prediction from raw pixel to depth map. Yeah, so here we use it as a geometry initialization. And we have a second phase. So we use a point-wise aggregation or point transformer. So we aggregate in a localized, say we are not focusing on the entire point. Say we just allow the model to focus on its neighbors. So we have a hierarchical design about how to do this aggregation based on the point transformer, and then we convert from the point map to 3D Gaussians, because 3D Gaussian require a more detailed representation. So we have to represent the shape of the ellipsoids and many other attributes, say its opacity and its scale, rotation. Yeah, so having the regressed 3D Gaussian, we rasterize at another view. We flatten from 3D to 2D, and we have a predicted target view, and we have the ground truth target view, and we do a comparison with back propagate the loss. So in this way, we can make the 3D prediction or 3D reconstruction into a single neural network, differentiable neural network. So we have a initialization model, and we have a point transformer-based aggregation model. So combine them all, which is differentiable during our training. So we can use the differentiable rendering as an objective function to update the model. So far we have introduced how we can build a 3D model differentiably. So you can imagine, give the monocular video from the user, and we can have its 3D map. But now we don't have the semantics about the input video, right? So ideally, if we know the semantic information or instance information from the monocular video, which will be definitely very helpful for the downstreaming 3D perception. So the next question in our previous work, still in the large spatial model, we asked, is it possible to track the cross-view semantic consistency to extend from 3D reconstruction to semantic 3D reconstruction? So that's a second question in our work. And we have the solution. Yes, we can track the cross-view semantic consistency. And here is our solution. Again, you can see in the upper branch, we still have the geometry initialization, and we have the point transformer to do fusion. But we have another branch. We have a multimodal 2D model here. So say we can, because it's very difficult to annotate the every 3D model, 3D scene, because annotating in 3D space is very, very expensive. So we rely on the lifting technique. Say we have so many 2D foundation models, like the CLIP, like the language-based segmentation. So it's possible to lift its feature from 2D, like this, to 3D. And then we can build the semantic 3D Gaussian in that way. That's our motivation. And indeed, we extend the 3D Gaussian to 3D semantic Gaussian. So we have the additional feature vector for each 3D Gaussian. So it's very straightforward. And so here for each feature vector, it is derived from the 2D feature maps. And we have the point pixel aligned prediction. Say every pixel, we will predict 3D points, and each 3D points will have the feature vectors. Yeah, so here, we flatten from 3D to 2D, but now we are not only obtain the images, we not only have the pixels, we also rasterize the feature map at a third view, at a target view. And we optimize based on the feature difference and the pixel difference, and optimize the model in a differentiable way. But here we will frozen the multimodal 2D model like the CLIP video encoder. We will freeze it, and we only update the geometry initialization and cross-model fusion. And let's take a look at why we do this kind of fusion. Why we do not just use the per view prediction. So here is our answer. Say if we process the image one by one, because everything is in 2D, so we will see a problem. Let's say if we do non-view synthesis, we will see the inconsistent prediction. So the frames will flickering. And if we can lift from 2D to 3D, we can aggregate them and make a consistent 3D rendering, just like the red way in the red video. So here is our goal. So trying to use the cross-model fusion to make the inconsistent 3D to be consistent. Yeah. So here is with a little bit details of our work. So again, with the inputs, we first initialize the geometry, and we have per pixel prediction about its appearance and geometry. Here we tokenize is the appearance tokens, and we initialize the appearance token, geometry token. And in the lower branch, we use a pre-trained visual encoder, say the visual encoder from Clip or Aerosat, both works. And we have a tokenizer. We tokenize the feature into a set of 2D tokens. So having these 3 set of tokens, we do the aggregation. So we will compute a semantic to 3D attention. We will try to fuse semantic information, semantic feature into the appearance and geometry. And here we augment it with the as semantic aware features. And finally, we will render at a third view, so which can help us to formulate the loss. So the key idea of this work is very straightforward, but very helpful. We just have the geometry and the appearance initialization, and later we try to fuse the pre-trained 2D encoder and make the feature to be semantic aware. Yeah, and during the inference time, yes.
Could you give a brief description about the tokenizer that you are using? Like, is this a kind of a 3D tokenizer?
Oh, so you can think this is just using the convolutional kernels. We have one layer convolutional kernels to make to tokenize the 2D features into these tokens, and the kernel is learnable. Yeah, so with the string.
Okay. So you are dynamically doing that. Yeah. Okay. Cool. Thanks.
Yeah, just flatten the 2D visual feature to 1D token.
Okay.
Yeah.
Okay. So essentially, you are training the tokenizer as well during the training process.
Yes.
Okay.
Because this is just one layer of convolutional kernel, and again, we flatten from 2D visual feature to 1D tokens and fuse it with the previous tokens.
Okay, thank you.
So we use
And for the for converting the inconsistent 2D to consistent 3D, you're using Gaussians here?
Oh yeah, so we use the 3D Gaussian as a basic representation. And what we introduced in the previous slide is about the cross-model fusion.
Yeah.
After cross-model fusion, we will predict the set of semantic 3D Gaussian. Here is by regression. Say we use a model to do prediction, and it's not the traditional 3D Gaussian, because traditional 3D Gaussian is obtained by optimization, iterative optimization.
Yeah, I think so. It's a 3D aware visual tokens that you have, like the spatial view of fusion that you create.
Yeah, so in this, we will allow the not only the 3D map, 3D point cloud prediction, but also will have a more detailed 3D Gaussian and semantic feature perception. Yeah, which means the 3D map will have semantics, not only just the visual and the geometry.
Cool.
Okay.
Yep.
Yeah, let me move to the next page. So that's why during the inference time, so our work can do almost real-time inference. Say, give new images, unseen images in new scene, and we have a transformer model to predict the semantic 3D map, and we can render not only the RGB map, the depth map, but also the feature map at the new view. Say, give the image, we build a 3D model in a feed-forward path, we can do rendering. And with the feature, we can also enable some downstream tasks. Let's say the open vocabulary semantic segmentation. So here it is how it works. So define the open vocabulary. Say we have some categories that we are interested with. We can describe it, and we use a clip text encoder to encode the text input into embeddings, and we will compute the text to visual similarity, and then we can use the decoder from clip to decode the semantic 3D map. Yeah, just like this. So which means having a single neural network, we can build the RGBD with in outputs, and we have the 3D semantic 3D perception capability. Yeah. So we don't during this process we only require the camera pose annotation, and we even don't require the semantic annotation because we are doing the lifting from 2D to 3D. Yeah. And overall, you can think we require sparse 3D data, just a camera pose, and we build this machine learning model, and we use neural learning as objective. We collect a large scale data. So we train one model, we can allow the model to generalize in a zero-shot setting. So all prediction here is zero-shot setting. So just give images, our model can predict the 3D map in roughly 12 IPS. Yeah, so which means we make the semantic 3D perception to be near real time, a new semantic encoder. Yeah, so that's most likely of the first work before we introduce the VLM3R, because I want to give some context about how can we make the end-to-end 3D perception from images or from monocular video. And next, we do see a lot of concurrent work from many different institutes. So this work called Think in Space, developed from San-Yin and Dr. Fei Li. So they built a benchmark to evaluate how the large language model, multimodal language model that can see in 3D, remember and recall in 3D space. So here is their demo. So having the monocular video as input, let's say a room, and we can define some task, let's say the object counting. So how many sofas? And the agent, the multimodal language model will think. It will make the prediction, let's say 4. And they define roughly 8 tasks. And yeah, so each task is carefully selected and collect the data. So they have this data, and then they will try to evaluate the existing multimodal language models. So this is the overview of all of these tasks. So they define the task. First they define the category of these tasks, and they will have questions, and they define the answers. Yeah, so this benchmark is called VSI bench, Visual Spatial Intelligence. And I can say this is probably the one of the earliest work that focusing on studying the visual spatial performance, let's say based on monocular video without the requirement of depth information. But the point is, let's look at their performance from this paper. So this is the human level in the outside. And if we look at the Gemini and GPT, but roughly that's about 1 year ago. So you can see clearly they are significantly lag behind the human performance, right? If we look at the this figure. So I mean, among almost all of the benchmark, from appearance order, route plan to some metric depth estimation like the room size, absolute distance, the foundation model all lag behind the human performance. So that's a status of the development of foundation model for 3D perception. So we developed the Reconstruction augmented with the 3D reconstruction, and or we call it as VLM3R. So the idea is kind of straightforward. So having the monocular video, we have the visual token from clip. We also have a spatial encoder to decode to have the geometry token and the camera token. So we fuse them together, and then we preserve the dimensionality of existing vision language model, and we fuse them to large language model, and we do a lot of fine tuning. So that's a high level idea, and let's look at the diagram again. So having the question and having the monocular video as input. So previously, we only use a visual encoder, say it's either clip or DynamicVerse. but it's very difficult to allow them to perceive the accurate metric scale depth map, right? Because they are never trained with the depth as the objective function. But we introduced another spatial encoder from also another concurrent work called Carter 3R from UC Berkeley and Google. So they can export the geometry token and the camera token. And with these three tokens, we fuse them together. We do a 2D, 3D fusion. And this is how 2D, 3D fusion works. Again, just a very simple cross-attention operation. And we can fuse 2D, 3D information into the 2D tokens and make the token to be 3D aware. And we have a projector to align the dimensionality before feeding them into the language model. Yeah. So because we are trying to preserve all existing information from the visual part, from the language model, and we only want to introduce a residual learning from the geometry token, from the camera token. So the geometry token represents the overall 3D structure of this environment, and the camera token represents where is the current camera, or you can think of this is the camera pose, and the geometry token is about the 3D structure of its input. Yeah. So with this high-level design, yeah, go ahead.
Yeah. Sorry to interrupt, Zhiwen.
It's
I
fine,
can
yeah.
see here. Okay. I can see here you have geometry tokens and you have view tokens.
Yes.
Are they? Is the view tokens? I'm guessing the view tokens corresponds with the camera tokens. Yeah, it's the same.
So, you mean this V's token here?
Okay. Oh, okay.
So the video token is just like, let's say, for most of the lava-like model, we have a clip-like video encoder to tokenize the image-wise information, but they are doing the 3D. They are doing the parsing, semantic parsing, based on only semantics, and they don't have the per pixel-wise perception about the depth, about the spatial relationship. They only have the image-wise understanding. Yeah, let's say the clip, right? So that's why the motivation of our work to introduce another spatial encoder is, so we want to have the per pixel extraction about the depth information. And ideally we rely on a spatial encoder that is pre-trained with web scale data. And let's say based on the existing model called Duster, so we can extract the geometry token and the camera token from it.
Fair enough.
And so which means this branch is previous. Yeah, go ahead.
So in this high-level pipeline, is the cross-view semantic consistency coming into the picture? Is it enforced separately, or everything happens automatically? Like, how do we maintain cross-view semantic consistency in this?
Automatically. So this is the short answer. If we gonna to assume more pairs, it requires extensive post training. So that's why we hope to align everything automatically, and we add a residue. Let's say after the fusion, we indeed have a residue because we only need want to update a little bit about the previous latent space. Yeah. So we only have this fusion, and we also have a residue to allow the model to update itself. Yeah.
Okay. Thank you.
Thanks for the question. So yeah, the high-level idea is kind of straightforward because we are augmenting the video encoder with the spatial information from a pre-trained 3D encoder. And then with this formulation, we will have 3D perception capability of the existing language model. The second part would definitely about the data, because the data is a field. So how can we build the scalable engine for the data curation from the existing visual spatial data pairs? So first, we rely on existing data with both RGBD and semantic annotation. So because they have a very clean annotation, So we rely on the ScanNet and ScanNet++ and ARKit scene as our data source. So first, for each scene, we extract its point cloud, and we also have its RGB video, and we first do a sampling from the RGB video because we have a limited context window. So we sample about 32 frames from the input video, and we obtain its RGB depth mask and the camera pose. And we also obtain the camera pose for each sampled frame. So we will have a processing pipeline. So for each scene, we will have a scene metadata. So we will generate the room size, the center, the object count, the 3D bounding box. That's about the whole scene description. And we will also have another JSON for this annotation, for this data engine process. So we entered its frame ID, we entered its image path, we have the camera information, camera pose, and the 2D bounding box of the visible part of every instance from in 2D. Say project the 3D bounding box and with the mesh, so we can define which pixel in the current frame is visible. And having this processing pipeline, we build a spatial-temporal scene graph because we want to extend from the visual spatial intelligence to visual spatial and temporal intelligence. Yeah, so that's why we build a semantic, you can think it's a semantic spatial-temporal scene graph, and we connect each frame together to a unified representation. Yeah, so let's say we have 32 frames for each scene, and we build the scene graph based on all input data, and we curate the QA data. And I could say many friends from Meta, from NVIDIA, they are asking about some detailed annotation process of our script because we released the curated data, and it's the only open source data that align with the VSI benchmark. Yeah. And another part is about route planning because in VM3R, we build a large scale training data set. But the point is, so there is a task that from VSI bench called route planning. Just like they entered the route plan by human, they ask their authors and some volunteers to enter the route planning. So we develop a scalable way to use a simulator by habitat to enter the route plan. Let's say define the task from one point to another point, and we plan the route in a textual description automatically. Yeah, so we scale up the process and we create a large scale data about the route planning data, just like the VLM navigation work. But here we build a visual-based model to process the task. And let's jump to the result page. I think this is maybe the most important part to describe about the result of our work. So if we directly look at the last row, this is VM3R 7B. So overall, you can see the average score is about 60. And this is a closed source model, GPT and Gemini. That's roughly half years ago when we derived this table. So we can see clearly we rank the first than all existing open source model and closed source model. But of course, still there is a gap between the human level perception. So, but I'm going to tell some information based on the resulting table. So you can see this is a 7B model. It first outperformed not only the similar size model, but also outperformed the large scale model, say the 40B and the 72B. And it also surpassed the closed source model. And I will explain detail with the Ablation study later. But so the takeaway in this page on visual spatial intelligence benchmark. So it works better with the poster training and the new architecture design. And next, go ahead, please.
Yeah, thank you very much, Zhiwen. So I saw that VLM 3R was 7 billion parameters.
Yeah.
Do you have other models of other different sizes? Did you observe what the effect of scale on the model performance and stuff like that? Did you do any ablation?
That's a
Or
very
did you see if it goes smaller than that? It would be nice if you had a smaller, even smaller model, a model smaller than 7 billion parameters that could do almost as much as this. It would be nice. Did you experiment with that?
Yeah, thanks for the question. So the short answer is we only tried 7B due to the resource constraint because we mostly rely on the resource from our school to perform the experiment. And we only perform the 7B experiment. And currently, we extended it with the 3B and some new models, but we haven't released it. We haven't updated the archive paper. So the short answer is we will prove, so it will generalize not only to 7B, but also to a smaller model. Yeah.
Thank you very much.
Thanks for the question. Yeah, so the next part is we're going to extend the visual spatial intelligence benchmark to visual spatial temporal temporal intelligence. So we add a keyword about the temporal. So the temporal here generally means so how frames moves across a time dimension. Say, can we allow the model to track the dynamics about the camera motion? Yeah, so we define a new benchmark called VSTI. So we have the camera related information about the camera distance, displacement, and camera moving direction. And we have the camera object relationship. It's about its absolute distance and the relative distance. And we also have the defined object relative position at different frame. So you can see an example. So we have the question about how things change between the frame A and frame B, and something like this. So we define the new benchmark, and we call it as VSTI bench. So here is the short answer. So indeed, VM3R scale with the not. Yeah, go ahead, please.
Yeah, apologies, Zhiwen. So I just want to see if I understand the benchmark a bit better. So essentially, the same benchmark is made up of 3 parts: the camera to object, object to object. Right? It's the exact same benchmark.
Yes, that's the same benchmark. But previously, during the question, they don't have the frame identification. Say they don't specify from one frame to another. But here we have the definition about how frame changes, and we have some question related to camera object, and object to object.
Okay. Thank you.
Yeah, so that's why we call it a temporal, because this is monocular setting, monocular video, and the frame change means the temporal change. Yeah, so this is the short answer. So VM3R also outperformed the existing model, not only the open source one, but also the closed source one about the temporal awareness. And let's jump to the Ablation study. So we need to find the data and the architecture change very effective. But let's take a deeper look at how things works. So in the first row, that's a baseline model. The baseline model directly with the post-training using our data. So we can indeed see it already surpassed many previous work, say here. So if we don't tune the model, the performance is roughly 35. But if we use our data, our curated data pipeline to tune the model, so it directly jump to the 57. It's a significant jump. And if we include the geometry token, so here the without camera token means we only encoded the geometry token. So you can see with the geometry token, we further boost the performance a little bit. And if we include the camera token, we improve the model slightly. So combine them all, we achieve the performance at roughly 60%. So the takeaway in this application study is first, the post-training is the most significant part. So it's a data-hungry work. So as long as we have data, we can make the 2D model to have a very strong performance on these 3D tasks. And the next conclusion here is, if we have the camera encoding about the geometry encoding, we can further boost its performance, roughly at 3 points here, from the first row to the last row. And both camera tokenization and geometry tokenization works for our work. Yeah. So this is most likely about the VLM3R. So we already take the conclusion here. So spatial intelligence is also a data-hungry task. So that's why it is possible to create more data, but not only specified with say the indoor RGBD semantic data, which is highly inscalable. So here we going to very briefly introduce my last work, just 3 pages. So we have the images. Let's say this is the web scale images, and we have very, very limited 3D models. So how can we rely on the human video? Because human video is indeed 4D data. We have depth, we have 3D information, and we also have the temperature change. So how can we curate the 4D data from the in the wild video, say from YouTube? So here is our very new work. We call it DynamicVerse, which is published in New York this year. So we have a data curation pipeline. Say we combine the traditional 3D techniques and modern multimodal foundation model together. We can annotate not only the depth, the semantic, the instance information, but also we have the caption, the scene-wise, frame-wise caption from the input video. And here is the overview of the DynamicVerse. So in the last year, you can see we have roughly 100K data, videos, and we have roughly 13 millions of frame annotation. And we have a very detailed annotation about the innovative video from many benchmark data, from the most driving data, and from the YouTube data. So with this diverse source, every data here is from the real world. And here it's a visualization about the annotation. So this is from a benchmark data. We annotate not only the camera pose, but also the dynamic actors and the 4D mask about the dynamic actor. And we also have the general scene caption and the instance-wise annotation. Yeah, so that's most likely all my work from recent 2 years. Thanks for every attendee to listen to my introduction. Thanks. Yeah, any questions from audience?
So guys, are there any questions? Do we have any questions for Zhiwen? Are there any questions? Okay, so
Yes.
Okay, Ayush has a question. Please come off mute and share your question, please.
Yeah, hi sir. Like it was a very great session. So like actually I am new to the 3D part of the computer vision, and for some days I have been engaged to a project which for which I have to create a 3D model from 2D monocular videos of a construction site. So like I need some little bit like I have researched something and try to implement something like, but I am facing some challenge to extract geometrical aspect of the those like object like for the construction site and all these. So like can can you help a little bit like for in this?
So if I understand your question correctly, so you are asking help to annotate your data?
Yeah, like to extract the geometrical aspect of the uh, data. Like I have 2D monocular videos of the of some construction sites, and I need to create a 3D model from that, and with accurate measurements of the sites, like uh, wall size and floor and all this,
Okay. Yes. So you, but I'm not very sure about, are you asking suggestions or asking the?
Yeah, I'm asking some suggestions like to techniques
Oh,
for
yeah.
implementation like this.
Yeah. So if you are thinking annotating the geometry part, I would say you first maybe rely on the foundation model, let's say the map anything, the VGT, to first annotate a dense 3D map and use some traditional technique, let's say the boundary adjustment to make your prediction to be consistent.
Yeah, like I have tried the map anything thing, but the thing is that it requires the stereo vision data, like data captured from the like two cameras, and I have only monocular videos, like the camera rotating 360-degree videos. So that's the problem. That's why I'm asking like for any other thing is there.
So you have to also include the traditional technique to make your consent to align better, because this kind of foundation model make great prediction, feed-forward prediction, but you have to align them using traditional algorithms.
Like, can you name some of them?
Just boundary adjustment. Let's say you can revisit the work from the duster, and duster have a script to do the post-processing.
Okay, like
Yeah.
I'll try to this.
Yeah.
Thank you very much.
Yeah.
Thank you.
Yeah. Anirudh has a question, I think. Ayush, have your doubts been put to rest? You've gotten some ideas now that you can implement for your project here.
So I'm sorry. So I have a kind of back signal from the Wi-Fi. Can you repeat your question?
No, I'm talking to Ayush. I just wanted to confirm that he has gotten some ideas to help him with his project.
With which project?
I'm talking about Ayush. But
Yeah,
no
yeah.
matter, no problem. Okay.
Yeah.
So
Anirudh, please go ahead. Yeah.
So I have a kind of a high level question with regards to your VLM 3R and the recent work 3D to 4D. What are some kind of bottlenecks or challenges that you observe in scaling, like not in terms of like the in scaling in terms of the accuracy? For instance, the human benchmark is about 78, 77, and your models are at 60. Do you see any challenges or like key bottlenecks that needs to be resolved?
Yeah, I see 2 points here. So first, I don't think dual visual encoder is variable. Let's say currently we have a temporal solution. Say we have 2 visual encoder and we fill them together. But ultimately, we will definitely rely on just one encoder. So which incorporate the pixel-wise prediction and image-wise semantics and fill them together. Say ultimately, we don't need the fusion process, and we can parse all the required information from a single encoder. And the next would be, so still the current feed-forward 3D reconstruction model, we can have the density prediction, but the accuracy. So if we look at the surface, so it's still way below the expectation. So it's way below the traditional multi-view stereo with iterative optimization. So which means the geometry accuracy is still far behind the expectation and long way to go. Yeah.
Thanks. So if you just have one encoder, how does it take care of the camera tokens and all of that, which you mentioned?
Ultimately, I think some research team will develop a unified model, but maybe by distillation, something like that.
Oh, okay.
Yeah.
Well, thank you so much.
Thank you.
So that was actually a very insightful question. I myself do not really I don't really know how a unified encoder would work. Because then the unified encoder would have to essentially do the job of two encoders. You would have to learn the normal visual encodings that Clip learns, and then you would have to learn the camera encoding and the geometry encoding. So I think that's actually a nice question to ask, but I suspect that it would probably be a very data hungry project. To get one just one encoder that learns all that stuff will probably require a lot of data. So that is actually a nice project. I think someone here can perhaps take up. So I like that. Thanks for the question, Anirudh. I appreciate that.
Yeah. Thanks for the question too.
Yeah. So are there any other questions? Mayank, any questions from your end? You're muted. You're muted, Mayank. I can't hear you.
Okay. Yeah, I do not have any queries right now, but I really like the framework in which, like, the authors had the parallel processing. Like, they didn't use the final 3D point cloud from the cut 3R. Instead, like, you guys intercepted the rich implicit information, like the visual encoders that using the parallel processing to process the video to get the 2D appearances, and like the simultaneously the cut 3R, the spatial encoder processes the same video, and it gives you the internal representations. So like you have two sets of crucial tokens, like the geometry tokens and the camera view tokens, and you guys use those to fuse to the 2D visual tokens using the cross attention mechanism, and then use that in the downstream tasks. So like this kind of huge the whole process is kind of intriguing and very interesting.
Thank you.
Yeah, thank you very much, Zhiwen. I actually skimmed through the paper. I skimmed through the paper before the session, and I found that the paper was actually quite short. But I appreciate you taking the time to give us a lot of context, because the paper is actually built on previous work that we've done. Yeah, and just to read the paper alone would not have provided all of that context. So thank you very much for that context that you provided prior to discussing VLM 3R.
Thank you.
Once again, we would like to appreciate you for taking your time to share your work with us today.
Appreciate for this chance. Thank you.
Thank you very much. Once more, does anyone have any questions for Zhiwen? I think that there should be more questions.
Yeah, we can contact us later. Thank you.
Yeah. Okay, so in the absence of questions, we would like to thank everyone for coming for the meeting. We'd like to thank everyone for being here. Yes, and thanks you very
everyone, much. And best of luck for the ICCV.
Thank you.
Yeah. Take care, everyone, and bye till our next meeting then.
Bye.